guys, welcome. Hello, 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 hello. Hello guys, welcome to the new video. In this video, we will try to understand dynamic programming and so we will understand what is dynamic programming, how to approach it, and in this we will assume you have like some idea about programming and you have done some questions and you have understanding of recursion and data structures and you have solved some questions before. So if you have done that, then it will be a good journey. We will we are doing this for practice, or we can say revision, right? And on the way we will understand also how this works. So let's start with the introduction, right? Introduction. So the essence of dynamic programming is to avoid repeated calculations, right? So often dynamic programming problems are naturally solvable by recursion. So you will see mostly all of the problems of dynamic programming are solvable by recursion, or vice versa. Most of recursion problems are solvable by dynamic programming. Not all, but most of them. So in those cases, uh, when we are solving a problem by dynamic programming, so their recursive solutions are easy to write, right? So what we do with recursion, from recursion, let's say we go for DP. So in this case, we say repeated states, or we can say function calls, right? So how we do this? We add, you already know, or you have understand, we store those values in a table. We can say it a lookup table. Right. Then, so this process is called top-down dynamic programming with memories. So it's like top-down. Recursion is like this, right? And n minus 1, n by 2, something like that, right? It's like tree structure. So in a similar fashion, if we are going from recursion to DP, then it is called top-down programming with memoization. Top-down DP with memoization. So let's go with some examples. So most basic example we know is for classic example we have like a Fibonacci sequence. So Fibonacci sequence, its recursive formulation is like that: fn is equal to fn minus 1 plus f of n minus 2, right? And these it comes with some condition where n is greater than or equal to 2. It only works with it has some base cases. F of 0 is 0 and f of 1 is 1. So in C++, if we try to write the code for this, right? In C++, we can write code for this is like integer of function integer of n, right? Then we have if n is equal to 0, return 0. If n is equal to 1, return 1. Else we can return like this: f of n minus 1 plus f of n minus 2. This is the function for Fibonacci sequence in C++. It's a recursive sequence. Alright. So runtime of this recursive function is exponential, approximately order of 2 power n. So since one function call fn results in two similarly sized function calls, f of n, like we can say like f of n, f of n minus 1, f of n minus 2. So we write the recursive function for this is like f of n is equal to f of n minus 1 plus f of n minus 2. It goes like it is less than or equal to f of n minus 1 twice, right? And it is similar to order of 2 power exponential, right? As you all know, like f of n minus 1 plus f of n minus 2 plus 2 plus 1, right? So it is like n plus 1 by 2. It's of order of n square. This is how we calculate the time complexity for this. Right. Alright. Let's add some more pages. Okay. How we add in this? I am new to this tool, so what? Uh, how do I add a new page? Right, it's like this. So, how we can speed up this Fibonacci sequence with a dynamic programming, right? So our recursive function currently solves Fibonacci sequence in exponential time, right? It's order of like this. This means like that we can only handle small inputs values before the problem becomes too difficult. Let's say we have some f of 5, f of 6. We can handle these in a like limited time, right? If it is increased, if it increases the f of 20, then it will become 2 to the power 20. So it goes in millions, right? Right? Like to be precise, if we are calling f of f of 29, then it is going for around 2 to the power 29 calls. Then it will approximately it is 1 million function calls here. So it's infeasible, right? We should not go for this. We have to handle this. To increase the speed of this calculation, we recognize that the number of subproblems is only order of n, right? Which are f of 1, f of 2, f of 3, and f of 29. These we only need these values, right? So what we have to do, instead of recalculating these subproblems, we solve them once and then save the result in a lookup table. Subsequent calls will use this lookup table and immediately return a result. Hence, we would eliminate exponential work. Each recursive call will check against a lookup table to see if the value has been calculated. This is done in order of one time. Like so, each recursive call check if this value is already stored in the memoization table. If it is, then return that value. No need to calculate it. This lookup will take order of one time, right? If we have previously calculated it, then return the result. Otherwise, if we calculate the function normally, the overall runtime will be order of so with the memoization, overall runtime will be order of because we are doing only order of n calculations of function calls. So this is a very big improvement from order of 2 power n to order of n. Very much. So if we want to write code for this in C++, we can write like this. In C++, we can write like integer of f of integer of n and if first we have to make it array. So we defined const int max n is equal to 100. Let's say there are we supposed to calculate till 100. Uh, then we calculate a boolean array of found max n, and we define a memoization integers memoization max n, right? Right. These are the variables. If we found that n, then we return memo of n. If n is equal to 0, return 0. If into 1, return 1, right? Else return memo of n is equal to f of n minus 1 plus f of n minus 2. So this value goes into this n value, and if n is 0, so let me explain something like let's say if we are calculating for f of 5, right? So we goes f of 4, 3, 2, 1, right? So f of 5 is what? N here 5. It is 5 here. When it is 5, it is not. So this is, let's say. Let me zoom out of the meter. Okay. Okay. Let's say let's say I have this array 1 of size 5, 0, 1, 2, 3, 4 and 5. Alright. This is Boolean array also. Right. Like this. Alright. So now what we are doing, we have this index. This is found array. This is memoization array. First, these all are false, initialized to false 0. Right. Then what we will do is we have initialized f0 is 0, f1 is 1, right? Now what we are calculating is f5. Is f5 in this? No. So what we will do, we go if is n equal to 0, no. Is n equal to 1, no. Then we go for n minus 1, right? So here this fn minus 1 will call first, then we go for 4, then this will go for 3, this will go for 2, and this will go for 1. At the end, this will return f1 is return 1, so it is already 1. f0 will return 0, alright. Then these two calls will merge, and then f2 will become what? f2 will become 0, 1, 2, 3, 4, 5. So f2 will become what? This plus this. 1 plus 0 is 1. So we have stored 1 in the memories. Now also we have marking this here. Now when 3, what this will return 2, what this will return 1, 3 will become 3. This is worse. And this will now in this call, this has returned 3. This will go for this call, right? Now f of 2, this will check found of 2. Is this true? Yes. So it will return directly 1. This will not go in the deep tree like 1 and 0. This will not go there. It will return 1 from there. Is plus 3 plus 4 is 4 here, right? And then it will for 5 it will return 4. Now it will go for 3. 3 is 3 already there, yes. Found, yes. So this will return also 3, right? This will not go deep in the tree and do not calculate repetitive calculations. So this is going for this will return 3 and 4 is from here. We add them up. 4 plus 3 is 7. Alright. So with our this new memorization function, so previously it was making roughly order of 2 to the power 29 function, 2 to the power 5 calls, which is something like 32. Now it is making only f of 5, only 5 calls, function calls, right? Which are 1, 2, 3, 4, and 5. These are the all 5 calls it has made. Or we can calculate like this 6. This is order of 5, n, right? If we want to calculate this calls, because it is all order of 1, and rest of calls are order of 1 constant. So we have reduced tremendously, right? For if we are calculating from 2 to the power 29, which were something like 1 million, we drop to 29 calls, right? Or we can say also we are if we are saying like if we are calculating these calls or constant calls, so it will go something like 57 calls, right? So it's nearly like 20,000 times fewer function calls. So now one more thing is, one new thing is, we are now limited by our data type, right? So f power 46 is our last Fibonacci number that can fit into a signed 32-bit integer. So it is last Fibonacci number which can fit into a signed 32-bit integer. Right. So let me increase this font plus a little bit more. Alright, it's good now. Alright. Alright, it's good now, I think. So typically we try to save states in arrays if possible, since the lookup time is order of 1 with minimal overhead. However, more generally we can save states any way we like, right? So other example include binary search trees. So in C++, we can save, like not in C++, like in general, we can, here we were storing the states in array, right? So now if we don't want to save states in array, we can save those in binary search trees, right? So in C++ it's like map, or we can store in tables. Map in C++ here, and it's like this map is unordered map in C++, right, like this. We can say like orange, right, custom colors. We can add some custom colors like this. Okay. Right, so how we can save this is unordered map of it, like manual. So it will, we can like if int f int n if memo.count is n, then return memo n, right? So what count function do? It tells like if it is this value exists or not, right? Also one more function we have in this what count function do in unordered map and C++ is
the count function in C++ maps used in Android. Returns one of the keys method.
so this count function what it will do, it checks if a key specific key exists or not, because each key is, in standard map must be unique. So the function returns either 1 if key exists or 0 if key does not exist. So it is primarily used as a way to verify if an entry exists before trying to access it. Right? So time complexity of His algorithm complexity is of log n. So for this we have time complexity of order of log n. So if we are doing so let me write full algorithm first. Then I will talk about this. This is one more thing. And if n is equal to 0, 0, return 0. If n is equal to 1, return 1. Right? Else what we do, return for key n we are storing value f of n minus 1, f of n minus 2, like that. This is of order of n log n. So overall time complexity will become order of n log n, right? Which is no better than order of n we have in array. Also we can, this was unordered map. It is using S no, it has like because we were using unordered map, right? So the lookup for this is like order of 1. So it will become order of n only. But and we are using hash data structure here, right? Similarly, what we can do here is we can use map as a data structure, like this. So like this, right? So both of these will almost always be slower than array-based version. So here, like in map.count function, this is a binary search tree, right? This is based on binary search tree. So this lookup is order of log n. So time complexity for this will become order of n log n, right? So these alternative way of saving state are primarily useful when saving vectors or string as a part of statements. Right? If we want to save, let me say, if we want to save some state as a integer, then array is used. But if we want to save vectors or strings, then array is not that useful. We can use this hash based like unordered map or map. Using a binary search tree, we can say map in C++. To save state will technically result in order of n log n, as lookup and insertion will take order of log n. And order of n Unix subproblems we have order of log n time. So this approach is called top down. Right? As we can call the function with a query value and calculation start going from top to bottom. Right? Top is queried value and bottom will be the base cases of the recursion, and it will make shortcut by memorization. Right? After this we have another approach which is called a bottom up approach. Bottom up dynamic only seen top-down dynamic programming with memoization. We can also solve problems with bottom-up dynamic programming. Bottom-up is exactly the opposite of top-down, right? So in this you can start at the bottom, which are the base cases of the recursion, and then we will extend it to the more and more values. To create a bottom-up approach, let's say for Fibonacci numbers, we initialize the base cases in an array, then we simply use the recursive definition on an array. Now how we do this? Let's say we can in C++ we can define const of an array like int max n is equal to 100, right? And we have defined an array int of fib max. So what we can do? If we call a function f for n like this, what we can do is we initialize this fib 0 as 0, fib 1 as 1, and we try the loop, for loop right here. Let's take this color. For int I is equal to 0, 2, because 1 and 2 we already defined. I is less than equal to n, I plus plus, and what we do is fib of I is equal to fib of I minus 1 plus fib of I minus 2, right? And what we do is we return fib of n. So let's take an example. So what we are doing here is we so let's take the example here. We want to do F5, then what we will do? We have a array, right? We have this array. Right? 0, 1, 2, 3, 4 and 5. Is 0, which is initialized to 0, this is 1, which is initialized to 1. We need these. So our for loop will run here. 2 is f of 2, is f of 1 and 0, plus this is 1. Then similarly this is 2, this is 3, and this is 5. Right? Then we come this f of 5 is return, this will return 5. This is very simple. It's of order of linear time, it is order of n strictly, and space is of order of n. We can now, alright. Now what we are doing here, we do repeated work if we call the function more than once, right? Secondly, we only need to use the previous two states, right? We only need f of I minus 1 and f of I minus 2. So we are jumping in a competitive programming domain here to save more time on space complexity. Right? So what we were doing, f of I only depend on f of I minus 1 and f of I minus 2. Only two states, previous states. So what we can do, we can reduce this space complexity of order of n, from order of n to order of 1 constant. How we do this? This is the example of bottom-up dynamic programming. solution for Fibonacci sequence which uses only order of one memory. So this could be like this. So we have int max. We define a constant int max is equal to 3 because we only need two states for a third state, right? Previous two states for next third state. So only three states we needed in a memory to be present. So we can define it like this, and fib of max n like this, and we can define the function int of function n, int of n, fib of 0 is equal to 0, and fib of 1 is equal to 1, right? Now our for loop will run. For of integer n equal to 2 to n I plus plus. Now what we can do, fib of I modulo max n is equal to fib of I minus 1 modulo max n plus fib of I minus 2 modulo max n. And this is a very critical part. Return fib of n modulo max n. So to understand it better, we can take this example of let's say we want to calculate f of n. So we only need three, f of 5 we need. So we need 0, 1 and 2. Max n is 3, alright. This is nearest to 0 and this is nearest to 1. Now loop will go from 2, 3, 4, 5, right? We want to calculate f of 2, right? So f of 2 depends on 1 and 0. So f of 2 modulo 3, we take this this equation only. We want 2 modulo 3 is 2 only, and this will result in 1 modulo 3 is 1, 0 modulo 3 is 0. So this will add up and it will go to this 1, right? Now we want 3 modulo 3 is 0. So we will save 3 in this index. It will depend on 1 and 2, right? 3 depends on 1 and 2. So we have 1 and 2 here, right? So then, and 1 modulo 3 is 1 and 2 modulo 3 is here 2. Then it will become 3 here, right? Now for 4 modulo 3 is 1. So we save 4 here, right? Now it will depend on 3 and 2. 3 modulo 3 is 0. So here this index, and 2 modulo 3 is 2. So this and this, 2 and 0, it will depend on, and basically in algorithm wise 3 and 2. So 1 and 3 is 4, right? So 1 and 3 is 4, right? No, this was 2 here, and 1 and 2 is 3 here. Then we go for 5. 5 depend on 3 and 4. 3 and 4 we have 2 and 3, so it will go for 5. Now come to the return part. F of n modulo 5. So n is 5, modulo 3 is 2. We will return this value. So we will return 5, which is the correct answer. So this is how we were able to optimize space from order of n to order of 1, and time from order of 2 power n to order of n, right? So this is a bottom up approach. Updating. Bottom up is iterative, right? And yeah. So we are using this model trick to maintain the values only those values we need. So this was the basic of the Darwinian programming. So basic, what is the basic? Don't repeat the work you have done before. So one of the basic trick to get better at dynamic programming is do some classic examples, right? So classic examples in dynamic programming are like 01 knapsack, subset sum, longest common subsequence, right? And longest common subsequence, I think, and we have longest increasing subsequence. These are classic examples, and this is counting paths in a 2D array, right? And 1, 2, 3, longest path in a DAG, directed acyclic graph, and one more is longest palindromic subsequence. The one is road cutting. This is very classic. You can find these in every textbook. And at a distance. These are the examples you can find any DB textbook, or we can precisely any good DB textbook. These are the classic examples of dynamic programming to alright, and we can practice most important trick is to practice that we can practice related problems, the what topic we have studied, so we can study those. This was the basics of DPI. We will do some more things here tomorrow, or we can say next video, and in that video what we will do, we will let's see if I have those notes. I was working for DP. Alright, I will told you those notes when we will do the problem, right? Alright. So thank you so much guys for watching this. Hope you enjoyed it. was not recorded, but I have the alright. Hmm. Audio recording. Okay. Used. Why not? Why it's not? This is not working. Pressure is not working, guys. I am trying to start this audio recording. I don't know why it is. Alright. I think this is working, right? So OBS is working, so I have